So I'd just like to thank these various companies here that I've had dealings with over quite a few years that have been active in exploration on this margin, that have provided some of the seismic data that I'm going to use in this talk. So here's a big map of the whole margin to begin with, and you can see that I've highlighted with these three black boxes the larger discoveries that have been made in the last 30 years. So we've got, from the north to the south, we've got Cap Juby in here, which is along the Carbonate Bank, which has got, we don't know really how much oil is in place, but something like 250 million barrels. The Chinguetti area in the Mauritanian Salt Basin with something around about 1 billion barrels in place. That's currently producing from Chinguetti, and these other fields that will be coming on stream. And then this very large undeveloped area of Dom Flora and Dom Gia down in Guinea Bissau Senegal area, where we've got at least 1 billion barrels in place that's undeveloped because of the heavy oil, biodegraded. So we're looking at some pretty appreciable reserves scattered through there, but in fact no really dramatic production at the moment. The only thing that's producing is the Chinguetti field in here. Now, as I say, we've had one well in deep water in the last 10 years. So it's an amazingly large part of the passive margins of the world that's been very poorly explored, that has these rather large indications of oil and therefore good source rocks. The other thing I'd like you to note on here are the salt basins that you can see draped along the margin in orange. They're certainly a focus of attention, creating structure and seals, etc. And that's where most of the oil has been discovered so far. So all of those basins, we think, are roughly the same age. I'll be talking about those in a bit more detail later. And also you can see some up in Morocco, these rather large faults that come through the margin there. This, the northernmost fault there is the southern tip of the Alpine orogenic belt, where we have large overthrusting towards the south. So all this northern area of Morocco is very heavily thrusted and folded with subtly divergent thrusts. And there's been very little exploration in there, because the seismic is so awful trying to see through the thrust belt, you can't really see what's underneath it. So there may well be some interesting hydrocarbon discoveries to be made up in here. We can get better seismic and better structural understanding. We've also got these very large strike-slip faults through here, South Atlas Fault and the Middle Atlas Fault. These very large faults have got offsets that splay out into the offshore and create quite a lot of structuring there in southern Morocco. So next one, Scott.
So that's the left lateral motion?
It's been in at least 2 different directions, the motion, at various times. So through the Paleozoic, through into the Tertiary. So here's a rather simplified strat column for the whole margin. I think it works pretty well. There is a fairly similar stratigraphy throughout northwestern Africa. We start off in this early part of the sequence in the Paleozoic, just highlighting the fact that there are very good source rocks that are present throughout northern Africa. They're particularly well developed in the Tabla Basin in onshore Morocco, where there's not really been much exploration, with very high TOCs, world-class source rocks in the Silurian. But there's not a lot of exploration going on down in the Paleozoic. Most people are interested in the Mesozoic section. So the first thing that happens in the Mesozoic that I'll talk about in a bit more detail later is quite a long period of rifting in the Triassic. This is extremely well dated by Paul Olsen, who world-class research has been done on magnetic reversals all the way through these Triassic basins, both in the USA margin and in Canada and in Africa. So we have an extremely good timeline there, and we know exactly when those things started, around 235 through to 200 million years. After that, we have a very important event, which again I'll talk about in a bit more detail later. The salt being deposited when the first marine incursion comes in, around 200 million years. And the reason we know it's 200 million years is very fortuitously there are basalts erupting below and above the salt interval. So we can time the salt interval perfectly from the dates on the basalts. The basalts are dated at 200 million years plus or minus 1 below, 200 million years plus or minus 1 above. So we know within the geochronological area of 1 million years, the salt is deposited at 200 million years, which is the same story for almost every salt basin where we do have dates on the actual depositional interval. It's less than 1 million years. You look at the Mediterranean salt, that's 300,000 years. Present-day salt depositional rates are the orders of centimetres. So we think all our major salt basins in the world, and including this one in northwest Africa, are deposited with a click of a finger in geological terms in hundreds of thousands of years. Very, very quick deposition, which requires a big hole. So the Triassic rifting is underfilled, and the salt is filling in to pre-existing topography because we cannot subside the basin quick enough to allow 2 kilometers of salt to deposit in less than 1 million years. So, next thing that happens is we have a switch off of continental sedimentation to marine sedimentation, and there's a very well developed carbonate bank that runs all the way up the Northwest African margin, all the way up the US margin. It's been explored sporadically and with limited success. There are still lots of well-defined amplitude anomalies along the edge of that carbonate bank that have not been drilled, both on the US margin for reasons of the moratorium through nobody's allowed to drill on the east coast of the USA, but also just a lack of interest really on the Northwest African margin. People are returning to look at this carbonate bank in more detail now, and hopefully we'll see some wells going down into the carbonates in the next 2 years. You can see we've got source rocks in here as well. These source rocks are pretty important in the Toarcian and the upper Jurassic. They're local, rich in some places, not in others, and that's one of our big difficulties. We don't have a lot of seismic data. We don't, that's looking down into the deep part of these rifts. The data's pretty poor. We don't have a lot of wells, so we don't really know how good these Jurassic source rocks are along this margin. We do know how good this guy is up further north. This is a world-class source rock. This source rock was so rich and so thick that it actually changed the world's climate. So there was a dramatic drop-off in CO2 levels in the mid-Cretaceous, and that is the attribution of that drop-off in CO2 is a tremendous amount of deposition of source rock along the north, just along the Northwest African margin in Cenomanian-Turonian times. So it's getting up to 20% TOC and hundreds of meters thick. It's a very unusual source rock. So that's the potted history in a nutshell with all the ages on there. Finally, you've got the alpine orogeny that affects that northern part of Morocco, the Canaries volcanics coming in. So let's have a look at the real rocks now rather than a time chart and see what we've got. So here's the real rocks in the Moroccan Atlas. This is the red, in this case it's red bed sequence of Triassic rotated. You can see the beds there rotated round to 30 degrees. High amounts of extension locally in these troughs developed on shore that are extremely well exposed in Morocco. But unfortunately, most of what we've seen so far is red beds in Morocco, with continental lacustrine red beds, shales, silts, and sandstones. The next one. Yet another one to show you the rhythmicity. And this is just a plug for Paul Olson's work. If you've never read any of Paul's papers, he's actually tied all these cycles that you can see in here to Milankovitch cycles and got paleomagnetic reversals all the way through these sequences. So every one of these sequences is dated to within about 30 to 100,000 years. And this is back in the Triassic. We've got that kind of accuracy on the stratigraphy. It's absolutely amazing. It's a lot better than the ages you've got in the Gulf Coast of Mexico in the Mesozoic, here in the Triassic. So the next one. So here it gets a bit more interesting. We've just seen red beds, but if you go across to the USA margin, some of you may well know these basins like the Newark Basin, the Hartford Basin, onshore US. These are wonderfully rich source rocks that you have in here that are again tied to Milankovitch cyclicity, and you get these very well described rhythmites through here with a rich organic source rock and a lower of my laser pointers.
That's the button right there.
Great. So yeah, you can see this seismic, these rhythmites through here with very rich source rocks. What you also see is a nice cross-section through the basin. The basin's got enough depth of burial to probably for source rocks to be mature. You just don't seem to have any traps. There are no internal structures in here, and all the oil just bleeds out onto the edge of the basin. So we need some of these little horse blocks to be drilled, perhaps, and there may well be some small discoveries still to be made in the US. The next one. So just to highlight their richness, this is some good work done by the USGS survey. There's several onshore basins that have got this quality of data. Lots of specimens being analysed, and ways up here you've got TOCs up to 8% there in those Triassic rocks. That's both lacustrine algal matter and more coaling material. So you've got both gas and oil-prone source rocks within these basins. Extremely rich, very well documented, but totally unknown offshore. Nobody's drilled them, and we just don't know how good they're going to be. The next one. This is showing you all the rifts that we know of that are of Triassic age, from 235 to 200 million years. These are all extremely well mapped on the North American margin, and the ones with the black blobs on them are the ones that have got the good source rocks. So you can see we've got a clear climatic zonation here that's latitude dependent, where we cut off there, and everything north of here is red beds. Everything south of here has got nice good source rocks there. What do we know about the African margin? Question marks all the way along. There's not a single well drilled anywhere in northwest Africa that has drilled deeper than Jurassic. Totally unknown stratigraphy all the way through here. But a nice conjugate pair there could give us a good Triassic source rock all the way through this area, which may well be worth investigating. So up in the stratigraphy now, past the Triassic into this really important magmatic event, the Camp Magmatic Province, which stands for Central Atlantic Magmatic Province, very simply, with those ages that we had dated. And it doesn't look like this is a plume. It's some kind of weird, diffuse, elongate anomaly that we have in the mantle, which generates magmatism over a 4,000 kilometre long elongate zone that doesn't have a central centre of effusion, really. You can see there's quite a strong area here, but further south we also get some magmatism down in ways down in here in the Amazonas. So it's slightly warmer there, but there's magmatism that extends all the way to Portugal. This magmatism was probably the reason we had the Triassic extinction. So the Triassic extinction is right bang on this boundary at 200 million years. It was the biggest extinction in world history, I think. I'm not a paleontologist, but if you read sort of noddy books on paleontology, they'll tell you that the Triassic was probably the biggest extermination of species on the planet. And we think it's due to world climate change again, because of these huge amount of volcanics that came out. So we've had this long period of rifting in the Triassic that went on for something like 30 million years without really much happening. And then all of a sudden we get this big plume event, and then that weakens the lithosphere, and we get the thing going from rifting to drifting, and we go into the oceanic development stage. So I don't think it's a coincidence that immediately after this event we begin to form oceanic crust. We thermally weaken the whole zone, and it allows those remote stresses to take over and stretch that weakened, thermally soft lithosphere and produce oceanic crust. You see all the salt basins on here again, all draped all the way down, extending more or less the same distance. Sorry, Scott. Extending more or less the same distance as the magmatic province. I'm going to focus in now on just to show you the quality of outcrops in Morocco from the salt. We'll also look at the salt offshore. We'll just show you a wonderful set of outcrops that have just been published on in the high Atlas Mountains onshore Morocco, with the next one now. And these are some of the best salt diapage and Lockatong salt sheets you would ever see anywhere on a seismic section or in the field. So this has just come out in the Geological Society of London. It's online. It's not even actually out in the journal. And you see these wonderful outcrops with ridges of salt cutting through the Triassic and Jurassic sequence there. Big canopy there overthrusting with overturned beds, just like you get in the Gulf of Mexico. Overturned stratigraphy underneath these Lockatong salt sheets. So it may well be worth a field trip there if you're interested in salt tectonics. I've never seen a better analogue to the Gulf Coast of Mexico than that in the field. Next one. So this is highlighting an outcrop now that I visited a few years ago that's out on the coastline, going into the Essaouira Basin now, which is this one, where all the big black blobs of salt are. And this highlights the fact that a lot of these salt diapirs have got squeezed and they've actually got up to surface. So the effect of the alpine orogeny, which I showed you with the southern tip of the thrust was up in here somewhere. In fact, all of this area is still affected by alpine events. So remote stresses are transmitted through the plate, and where there's a weak point in the plate, which is where the salt diapirs are, they get squeezed and they all pop up to surface. So there is a problem in this offshore, of all of this offshore region, with very late compression going on, which is breaching traps. So a lot of the salt structures have got faults that go all the way to seabed above them. So be careful if you're going to drill them. You may well be losing your oil up to the surface. Next one. This is just highlighting that magmatic province again, just in a bit more detail, and showing it does extend further south into the Amazonas region in Brazil. So a huge magmatic province down there. But all of this area it's got this high level of activity, no real centre to it. So it's quite an unusual magmatic event. Next one. So following on about the magmatism, just talk about now we go to the ocean spreading phase. I'm not the first person to show this diagram. Well, this one is actually we generated ourselves, but people from Exxon have talked about this in the past, and names escape me, but this being the oldest oceanic crust in the world. So this old, I think you can lay claim to the US margin here, having the oldest oceanic crust at about 190 million years old. And I think it's sandwiched between the East Coast magnetic anomaly and the Blake Spur magnetic anomaly. The reason for that is this looks like a paired sequence of anomalies that lie over seaward dipping reflectors. So we know for sure that this one does. There are seismic lines all the way along the East Coast magnetic anomaly that show a big pile of seaward dipping reflectors created by subaerial eruptions. So this ties in with the idea that we already have this thermal weakening and a very large magmatic event here. That continues now with the spreading, so we get this linear magmatism of huge piles of volcanics, normally generated above sea level, generating our seaward dipping reflectors. And if you just press the button again, we'll just get an animation of the spreading jump. So this is the spreading center jump that left 200 kilometers of old oceanic crust on the US margin that we don't see on the Moroccan margin. So you look at the distance from the mid-ocean ridge to both coastlines, and there's definitely 200 kilometers of extra oceanic crust that's left on the US margin side. And you look on the Northwest African side, there are no seaward dipping reflectors. There is a magnetic anomaly that's called the S1 magnetic anomaly. Very sporadic, not quite as strong. And enigmatically, it goes onshore here. So I don't know what it is. It's got the same kind of shape. And people have said, that is definitely the same origin as that magnetic anomaly. Those two fit, and that's how we fit the margins back together again. But hey, there's something weird going on here. If this big magnetic anomaly on this side is actually going onshore and there's no seaward dipping reflectors. So I don't know what that magnetic anomaly is. It's got the same shape, but it doesn't look like it's got the same origin. There's definitely no seaward dipping reflectors anywhere along Northwest Africa. So we got this idea simply that you've left the stranded seaward dipping reflectors that were originally a paired sequence that originally belonged to Africa, and now it's been stranded on the American side. Next one. Moving through now to the Mesozoic stratigraphy and the sediments that are getting more interesting for oil exploration now. This is a Jurassic carbonate bank. I'm just showing you this one to show you how continuous it is. It goes all the way along this margin, even up into Portugal. 4,000 kilometers long, very well defined, the edge of that carbonate bank. Yeah, we've only had a handful of wells that have drilled it, and two of those found an appreciably large oil deposit in Cap Juby. So hey, there's a lot of mileage in having a look at this again. It's such a well-defined trend and doesn't have hardly any wells along it. Next one. Into the early Cretaceous now. So we drown our carbonate platform with a large input of clastic sedimentation. There are very big deltas of early Cretaceous age all the way along the Moroccan margin. We're not sure how big they are further south, but certainly here, all the way through Morocco and into this terrain here that's still disputed. Some people call this a Western Sahara or the Democratic Republic of Sahrawi, or it's Morocco. But this area is a huge area that's not been explored because of political differences and 30 years of inactivity in this area. And lots of indication of huge deltas pouring out. Next one. So these deltas look like this, where they're coming in from the coastline. This is from Sidi Boukta, which is just north of Safi. And you see the top of the Jurassic carbonates there. Doesn't look like it's an unconformity. We just switch off carbonate sedimentation and then input these shallow water, these are channelized sands in here. You go offshore and they become deep water turbidites. So we can go ways offshore, to 100 kilometers offshore into DSDP wells, and you pick up these well-developed turbidites of the same age. So very good evidence of a very large amount of sand being input into the basin in early Cretaceous times, yet nobody has ever played this play. The lower Cretaceous play has never been really drilled in the offshore. People have had a look at it in shallow shelf and onshore, but there are no deep water wells that have gone specifically for an early Cretaceous sand. Lots of opportunities here, I think. Next one. Then further up in this stratigraphy, our world-class source rock that changed the climate. Here it is. I'll just pull these off the internet. There's lots and lots of pictures like this that you can find with these world-class tar shales that have been biodegraded, but we're looking at things with 22 billion barrels in place in here, and these Cenomanian-Turonian rocks, and 15 billion barrels in there, and people are seriously considering mining this stuff, producing oil from these oil shales. This is a source rock that works in Mauritania, and also it may well work here in northern Morocco where it gets overthrusted. So the Cenomanian-Turonian, from what we know of the stratigraphy, is underneath the thrust belt, and it will be tectonically loaded from Oligocene times onwards, and hopefully generating lots of oil in northern Morocco. Nobody has gone for a play with that process of tectonic loading on top of this source rock because of the difficulties with seismic imaging below the thrust belt. Next one. Okay, now we get to the spicy bit. So I'm going to have an overlook at the geology there. Let's have a look in a bit more detail at the individual basins and a few typical seismic sections and highlights of what's going on. So the next one. Just a word first about geography and where we're looking. So this first slide, I'm going to be looking at the northern Moroccan margin. And the Mazaghan area in here, there are several companies that have picked up large blocks in here recently. Some of them actually in this room, representatives of them. And this carbonate bank is extremely well developed in here. And the hardness of the carbonates makes them very resistant to erosion. And they just grow up to the sea level, but they're not present in the deep water. And you're left with an upstanding area, still at the present day, after the Jurassic growth, that is 4 kilometers high. So there is a 4-kilometer carbonate escarpment that's been there for 150 million years, and it's just gradually being filled in by sedimentation for the next 150. It's not got there yet, so there's still a big hole that needs filling in. And just a word on exploration from another side here, cultural side. You remember the Portuguese, Henry the Navigator, a very famous school of navigation in Sagres in southern Portugal. This is how they started off. They were going down this margin, and Portuguese colony was first put up here in Mazaghan. So this is now called Al Jadida, the modern name of this town. This is a World Heritage Site. There are several World Heritage Sites down this margin. The Portuguese built cisterns like this, absolutely wonderful place you can visit. Orson Welles' film Othello was actually shot in there. So they got to here by about 1480, 1490, and then built the fort. And so that became a centre for further exploration further south. Next one. So this is the seismic section of Mazaghan, courtesy of Chariot Oil and Gas. Quite recent seismic data that's been shot recently. And you can see this really interesting carbonate play up in here that we'll have a look at in more detail there. So we come off the carbonate edge, and there's the first high block there, and then right down deep into the basin. And it even looks like this block here has actually slid off from there, and actually slid off and over-thrusted with the salt squeezed up in here and a lot of the salt sheets. And this salt, as I mentioned, there's a late squeeze in here, and even this surface here has been folded. So this guy almost made it to the surface, and there's certainly faults that breach that. So any trap you suggest on the sides here has got a large risk of breaching because of this late squeezing. I'm just going to show you these two slides here now, the potential plays that Chariot have been talking about. So the next one is going to just focus in on the carbonate high. Definitely looks like there are 4 sets in there, and a mound which is quite elongate, and here as well. This is not too deep to drill, and this could well be a well-developed carbonate on top of that block. The next one. So this was their attempt at a flat spot in here. This could be part of the Lower Cretaceous sequence. So they're suggesting the Lower Cretaceous fans in here trapped up against the salt dome. Just some of the things that have been picked out at an early stage in the Chariot data. Thanks to them for letting me show this. Next one. So next basin down is Essaouira. You don't get a choice of what colour you paint your boat in Essaouira. It's like, you know, the town planning, you've got to build all your houses the same and fit in with the local culture. You've got to keep your boat blue here. So the next one. So this is Essaouira, and this is outstanding in terms of salt tectonics, because we have a huge number of allochthonous sheets in here. It's not quite the Gulf of Mexico, but it's by far the biggest extension of allochthonous sheets that we have anywhere in northwest Africa. And you can see these sheets are extending for something like 50 kilometres across. There's been lots of wells drilled in here that have played up a Jurassic source rock and been limited success in small fields, but only 1 or 2 wells offshore in here drilled on top of the salt domes. And unfortunately, they look like the folds, the salt domes, were actually growing when the turbidites are being deposited, and all the turbidites just go around the salt domes rather than over the top. So we don't want to be drilling on top of salt domes that are actually growing when you're looking for a turbidite reservoir of the same age as the salt growth. So let's just have a look underneath these sheets now on the recent seismic data that's been shot by Kahneman's Energy, who've now been taken over, and Cosmos Energy now operate these rather large blocks in here. So these are my attempt at putting in the salt in pink. So you can see that the top salt is extremely well defined. The base, not so clear, but I'm reasonably confident it's going to be around there. Nice base there that's imaged. This is quite long offset data, about 10 kilometres offset. Some of the only data of that kind of length that's been shot by the world. And if you zoom in underneath where we are pretty sure the Lower Cretaceous sequence is, you can see these channelizations, and This is exactly what we expect. This is that big sand input that we have in early Cretaceous times. So we'd be looking at a Jurassic source in here, which would be quite deeply buried and risking going into the gas window. But unfortunately, with salt in the sequence, you always get a cooling effect. So where the salt is extensive like this, you get a cooling effect that usually cools down the pre-salt by about 20 degrees C per kilometre of a lot of the salt sheet. So these sheets here would give you an extra 1 or 2 kilometres of burial to still be in the oil window. You can see there are traps like this as well that may be trapped underneath this subsalt sheet there. Next one. This is almost like the Gulf Coast of Mexico for those that you've worked there, I'm sure many of you have, with these back rotations against the salt feeders and a trap underneath the overhang there. So that would be where we expect our early Cretaceous sands at that kind of level. And in fact, when you trace that level through on the seismic, it comes up to the seabed, and you dredge the seabed there and you find early Cretaceous sand. The Cameron's Energy guys have actually done that, and perhaps Omniman as well. They've had boats out here dredging to see what that stratigraphy was, and it's those Cretaceous sands that we hope are underneath us. Next one. So, next port of call is the Sahrawi Republic, or Western Morocco, whatever you want to call that. Area under dispute, a huge part of the coastline there that's about 600 kilometres long, with no exploration done for the last 30 years. And we hope this dispute will be resolved in the near future. It's been a long time coming. People are getting fed up of it, and the United Nations has got quite an effective North American envoy there that's trying to deal with this and get the two countries or factions to talk to each other and allow exploration in here. So the blocks are licensed and people have shot seismic but no wells drilled. And this here, Cap Bojador, is an area I'm going to show you on the seismic, but a bit more about the exploration of Northwest Africa now and show you the next one. Cap Bojador was for many years the southern limit of the known world in Europe. So we had this cap here with quite strong currents, and people drawing diagrams like this showing what was south of it with sea monsters and the like, which people very much believed in back in 1434. For anybody that speaks Portuguese, that's from one of the explorers that have been down and tried to go past that cap. He who goes past Bojador who goes past and beyond Bojador goes beyond pain. Yeah, so it sounds like a pretty awful place to go if it's going beyond pain. And he was the first guy that dared to do it and actually got round and discovered the area to the south, the next cap down, which is called Cap Blanc. And this is the seismic data through Cap Bojador area. An amazingly thick packet. That packet there is going down to 10 seconds, almost two-way time, but it's thickest. There must be something at least 10 kilometres of sediment piled on the margin there. And in other areas it goes down to 12 seconds of two-way time of the packet. And a lot of that is early Cretaceous in here. So we have our Jurassic probably here. This is my notional Triassic in this rotated fault block. Probably the edge of the salt basin being in here, because we do have evidence of salt in this area, though it's not very well known. Myself and Paul Daly from Cosmos published a paper on this a few years ago saying there are a few salt diapirs in this area. And the important thing is you're going to have gas here, I would imagine, and here oil. And this big fold that's created quite late on in the Cretaceous stretches all the way through the Cosmos energy blocks for about 100 kilometres. And it's got an amplitude of perhaps a kilometre or so. It's about 10 to 20 kilometres wide. Absolutely huge structure all the way along the margin. And the Jurassic source rock should be in the oil window around about here with a limited feed upwards into that fold. So I'd really like to see somebody drill that fold and see what's in there. Say we've not got any wells anywhere in this area at all. Next one. So our next stop is another World Heritage Site in Mauritania. This is the second oldest minaret working in the world in Mauritania. All the way along this northwest African margin, back in the 12th century through to the 15th century, there were very large populations of people that came in with the Portuguese, and there were Christians, Muslims and Jews all living together in all these villages, all happily living together. What happened? Something went wrong somewhere along the way. You know, it's a wonderful place to live with harmony of religions and a very enlightened place. This is where people were doing astronomy and writing equations whilst we were beating our heads together in northern Europe and not doing much. These guys were the world leaders in astronomy working out of northern Africa. Next one. So this is Chinguetti up in here, and this is the salt basin to the south of it. And you see the salt basin is where all the activity is, but there are some interesting plays further north too. And again, Chariot Oil have got quite a big block up here that they picked up after Donna relinquished it. Some interesting possible discoveries there. But most of the oil is focused in here, because this is where the big tertiary deeper centre is that dumped on top of that world-class source rock. So our Cenomanian-Turonian source rock with up to 20% TOC is happily sat under a tertiary delta in here, generating lots of oil. There are some interesting plays in here still, but I'll show you next. So the things that have been drilled are the top of the bumps, nice and simple, but this deeper section in the Cretaceous, middle and early Cretaceous, strap traps against the margin here, subsalt plays, nothing been done. So this is an example of Tullow Oil's acreage. Thanks to Alistair Cheney for allowing me to show this. And these Lockatong sheets are overthrusts as well. They've got nice subsalt plays, and that actually has been drilled, one of those, and came up with about a 1 TCF gas field. So you're having both gas and oil in here. Cenomanian-Turonian is probably in the oil window, but the Jurassic is in the gas window, and you're getting mixtures from both source rocks possibly. The next one. So this is showing you a very well-developed anomaly on the edge of the carbonate platform. So I mentioned this carbonate as being drilled once or twice, but this is a north-south and east. This is east-west and this is north-south with the same anomaly. How about having a go at this? It's really well defined along the edge and could well be karstic or a little pinnacle reef there. So we hope we're going to see some wells drilled into these carbonates in the not too distant future. Next one. Now this is one of the wells that they did think they were going to be looking for a carbonate. This is in the Donna acreage in Mauritania. And very interestingly, they came up with a silicious ooze in this mound that I've highlighted in blue. So that was supposed to be the little reef there on the edge of the carbonate platform, and it was a silicious ooze. Now I'm not seeing the results of the wells, but all I know is that it was a silicious ooze. So we don't know whether that's a sponge reef, or is it some kind of hydrothermal venting through here that's created silica in the seawater. So you're getting this buildup of silica there and an actual mound of chert. Watch out for that. You don't want to be drilling that kind of stuff. And it looks quite interesting when you see that geometry. Next one. So our last sort of explorer's slide here, showing the guy that actually made it round. The next bit of the voyage was from Cap Blanc down to the Gambia and Senegal area. There was a lot of slavery went on as well as just exploring. This explorer was actually driven by economics here and set up the first slave trading in Senegal. And here it was with Obama there looking out onto the door of no return last year, of where the slaves went out of that door and never came back into the boats that went across through Brazil and North America. Prince Henry was part and parcel of that, so as well as being a great explorer, he was actually leading the slave trade back in the 1400s. Next one. So to this area that the Italian explorer got to in 1453, here's the river, the Gambia River there. I'm going to show you a prospect at the front of the Gambia River, Alhamdulillah, which means thank God. And this really large prospect here, very big fold, that's something like 10 kilometres wide and perhaps 30 to 40 kilometres long. This is, I don't know if there's been a problem with Africa petroleum being thrown out of Gambia recently, I heard. So I don't know what's going on there. But a very intriguing prospect that you see on this next seismic line. Next one, Scott. And there it is, a big fold here that looks like it's at the front of the salt basin edge again. And wherever you get the salt underneath the carbonates, it's quite often buried and never gets through the platform. We know there's salt along this margin because here at the front, you get this really big fold and then nothing else, and then a bit further south there are actually salt domes. So I think this is the frontal edge of the salt basin here, and we're just reactivating the frontal edge, squeezing the salt at the pinch out there, and it folds very late on. You see the folding going right up into the Pallegine there. And these will be the targets. There's slightly brighter stuff in here. This is going to be roughly around late Cretaceous in here, I guess, and the early Cretaceous in here that's also got interesting, quite bright anomalies. So quite a big structure there that hopefully will get drilled. Next one. So finally, the southern edge of the salt basin. This was the Cora. That's not actually a prospect. That was actually drilled. That prospect is the well, with the only ones drilled in the last 10 years in deep water. Unfortunately, it was a dry hole. This was in the AGC area, which is an area shared by both Senegal and Guinea Bissau. Let's have a look at that dry well. So it's out in this area in these folds where we have the Cenomanian-Turonian source rock that should be in the oil window, but it's only marginal in this area. And I think that was one of the problems here, was not only there wasn't a reservoir, but possibly this source rock was immature, whereas the Jurassic down in here is going to be generating gas up here. On the shelf, interestingly, there's enough sediment to actually generate the major oil deposit from Don Floor with 1 billion barrels of oil in, can actually come from the Cenomanian-Turonian. There's enough shelfal deposit there to put that source rock into the oil window. So let's have a look at this well that drilled in the deep water, the Cora well. And there it was, really nice looking amplitudes which die out down dip. So there you could actually draw yourself an oil water contact. But in fact, what looked like a soft was a hard. This was Albion limestones in here and clay stones. So that really bright stuff there is just limestone and clay. Bit of a shocker for them, and really interesting looking prospect that just went against the grain and wasn't a nice soft sand-filled oil, sand and oil and sand there. Next one. So this is the last slide, the technical slide, just showing you what happened with failures in Guinea-Bissau now. Lesson to us all, this one, pay attention. This were the two wells that drilled. This is the salt diapir here with the top clearly imaged. The interpretation was that, teardrop shape on our diapir, very poor seismic data, shot with a 5 kilometre long cable. This is time migrated, no attempt at depth migration here. They drilled the first well, hit the top of the salt here, carried on drilling to get to this target in the Albion, drilled another 2 kilometres of salt. Okay, let's sidetrack here, we're definitely going to be out of the salt here. Drilled another 2.5 kilometres of salt. All of that, the original well and the sidetrack are in the salt. So what we're looking at here is just over-migrated multiples from carbonates in the shallow sequence. Up in here, there are tertiary carbonates in here, and they generate a lot of ringing through there, and then it gets over-migrated. All you're simply doing is pulling the reflectors further and further in with over-migration because the velocities are faster, and you bring them in until they actually cross over deeper down. Ridiculous to think that's real data. There's no way you get a reflection back from a 5 kilometre long cable length out there. You need 14 kilometres. So they then drilled a well here, and that was a success. But they found oil. But hey, we're looking at somewhere that's probably 10 million barrels in place. Okay, we just drilled down the side there with a little uplift, and very good source rocks and very good sands. So what we're talking about here is world-class source rock again. World-class Albion sands everywhere, And people just drilling on top of salt domes or down the side of them. Let's try something different. Strap traps or something deeper down in the section which could be away from these little traps that you just get up the sides of the salt. And we hopefully will see some activity in here. It's a pretty big basin. Premier did this 2 or 3 times in this area, drilled through salt and settled into the sediments, and then walked away from it. So there's, I think, Svenska Petroleum and somebody else in here now. Last one, I think. So my message here is I've got to be an optimist somewhere in front of you guys, and there's a lot of optimists in this room as well. Being realistic though, this is the problem, is how patchy and unpredictable this Jurassic source rock. We still don't have a handle on that. We know it can be pretty rich in some of the onshore wells and in the outcrops, but what happens offshore from one individual half graben to another, it's going to change. Remember, the basin is still rifting during this early Jurassic period, and we're going to get a variability because of each rotating fault block has different water depths, etc. But this is an outstanding feature for me. Early Cretaceous sand, we know it exists and nobody's had a go at it yet. Those traps or structural traps. Jurassic Early Cretaceous bank, that has got very good bright spots that still need testing. And in Morocco, when it boils down to it, the failures are because they didn't find sand. This is a huge basin where we know sand's pouring in. There's got to be some sand in that basin somewhere. We just need to spend more time looking at better quality seismic and drilling it. And then further south, failed wells in Guinea Bissau have just been drilled on the salt domes, and nobody's drilled a single stratigraphic trap anywhere along the whole of the Northwest African margin so far. And then those are sub-salt plays in Mauritania and Essaouira. And that's it. Thanks.
Want to entertain some questions?
Certainly, yeah, as long as they're not too difficult.
As long as they're not too difficult. Jim Tucker.
What's the